Hello there and welcome back to this video series on control systems. For the past few videos, we have been looking at several aspects of frequency response. In specific, we have seen how frequency response techniques have advantages over time domain. We have seen Bode plot construction, gain margin, phase margin we have defined, and we have seen that Bode asymptotic magnitude plot can be used in approximating experimental data, and then you can find transfer function from Bode asymptotic magnitude plot. In this video, we'll try to see how design is undertaken. We won't go into the details in this video, but we'll show some preliminaries, that is how to go from time domain to frequency domain and vice versa. What is the overall philosophy of design in frequency domain? Very useful if you watch videos 55, 56, 57, 58 and 59 before going into this video. That would be really useful. You can make the most out of this video. After watching this video, a student will be able to specify how a Bode plot can be used to design lead and lag compensators, at least in some bird's eye view kind of sense. At least an outline of it can be specified. The compensator design can be done either in time domain using the root locus technique or in frequency domain using Bode plot. Each method has its own advantages and disadvantages, and in this and subsequent videos we'll try to see how we can use frequency domain method using Bode plot. Let us take a look at it slowly one by one. To begin with, we see that to improve the transient response, we use a lead compensator, and for improving steady state response, we use a lag compensator. We'll see what is this lead and lag compensator in subsequent videos. And we use a combination of lag and lead compensator to improve both. In frequency domain also, we use more or less the same approach, but the specifications for the controller are given in a slightly different way. We'll try to see what are the specifications in time domain, what are the specifications in frequency domain, and we see how we can go from one to the other. Frequency domain, we specify the requirements in terms of slightly different terms. Let us see what are those. We say these specifications in terms of gain margin, phase margin, gain crossover frequency, phase crossover frequency, bandwidth, and resonant peak. Using these requirements, we try to reshape the Bode plot of the open loop system to meet these specifications. Obviously, this method can be used only if open loop frequency response data is available. And also, this is applicable only for minimum phase transfer functions. Know that time domain specifications are usually specified for transient response in time in terms of percentage overshoot, peak overshoot as we call peak percentage overshoot, the formula for which is given. We are very familiar with it. And then settling time is approximated as 4 by zeta omega n, where zeta is the damping ratio and omega n is the natural frequency. This 4 tau is for 2% tolerance band. Also, the rise time, the first instant at which the system response cuts the steady state response, represented by TR, is given by this. Along with this transient response specifications, usually this position error constant, velocity error constant, and acceleration error constant may also be defined. In frequency domain methods also, you have certain specifications, that is resonant peak, then resonant frequency, bandwidth, and these are the formulas which can be used to compute this bandwidth, resonant frequency, and resonant peak. We know that systems with large bandwidth have small rise time, but they may pose problems if there is noise involved, sensor noise. There is a trade-off in there, and we'll see it as and when we come across such a situation. This and subsequent slides, we see a bunch of complicated looking formulae. For example, this bandwidth and resonant frequency and resonant peak. It would be helpful to memorize them. We have seen this time domain specification, peak, percentage overshoot, and then resonant peak, and we saw that both of these depend on only the damping ratio. You can go back and check on it once again. Because they are dependent only on damping ratio, we can plot how they look like with damping ratio along x-axis and percent peak overshoot or resonant peak along y-axis. This red plot shows the peak overshoot and the blue shows the resonant peak. So there is a relationship between both of these. We'll see a bit more about the frequency response specifications. There are other terms such as gain crossover frequency, then phase margin. We see that this phase margin, this formidable looking formula, it depends only on damping ratio. Hence, it decides the peak overshoot. So in a problem, if you are given percent peak overshoot, first find what is the damping ratio, and using this damping ratio you can find what is the phase margin. You can see that this curve between damping ratio and phase margin is more or less linear in the region from 0 to 0.5. You can see that this is a straight line up till this point. Within this region, you can approximate it as this damping ratio is phase margin by 100. That is the approximation given. Given this damping ratio, you can have a relation as shown here between the gain crossover frequency and omega n. Hence, this omega gc decides the rise time in the case of a step response. Or we have seen transient response specifications such as peak overshoot, then rise time and settling time. The steady state specifications usually involve position error constant Kp, and this Kp can be inferred from the body plot. If the system is type 0 system does not have any integrator in it. If the system is type 0, you have a flat portion in the low frequency region. Find out what is this flat portion. For example, this is 20. You say 20 log to the base 10 Kp is equal to 20 to evaluate what is the position error constant. This velocity error constant can also be computed for type 1 systems. You extend the initial portion of this body plot all the way till it meets the 0 decibel line. That is the value of kV. The frequency at which it intersects is the value of kV. So it can be very easily found out once the body plot is given. Similarly, the acceleration error constant Ka can also be found out for type 2 system. Again, in the body plot, you extend the initial portion of the straight line all the way till it meets the 0 dB line, and Ka is equal to omega square, where omega is the frequency where it meets. Note that all the three steady state constants depend only in low frequency region. See, you are using limit s tends to 0, that is very low frequency region. In trying to use the design techniques using Bode plot, it helps to identify what are the frequency regions. There is a low frequency region shown here. This is much lesser than the gain crossover frequency, and this region decides the steady state behavior. Just you need to remember, steady state behavior is decided by Kp, Kv and Ka, and all these are evaluated at low frequency. So this region much below the gain crossover frequency, that is low frequency region, decides the steady state behavior. The second region, intermediate frequency region, this kind of decides relative stability. This frequency region is around the gain crossover frequency. This kind of decides relative stability and transient response. The third region, high frequency region, in some sense indicates the complexity present in the system, and what happens to noise. That kind of things are decided by this high frequency region. Region 3, the gain should be very low to attenuate the noise, and we need to be very careful. We should not lose the signal but lose the noise. So we need to be very careful about this region 3 also. To consider three types of compensator. One is a lead compensator. The form of lead compensator looks like this: a 0 in the numerator, a pole in the denominator, and a constant term involved. You can write this as 1 over tau and 1 over alpha tau, where alpha is less than 1. This, when you express it as sinusoidal transfer function, you will have something like this. You can see that because alpha is less than 1, the magnitude and phase contribution of this term is lower than the numerator. So numerator leads in phase. That is the reason why we call it lead compensator. So you can see that this K dash is alpha times K. The lag compensator is also of the same form, a 0 and a pole. However, this beta is greater than 1 in this case. So the denominator contributes more phase than the numerator. That is the reason why we call it lag compensator. However, we don't use it for that purpose, for lagging, output lagging the input. If we want to derive both the benefits of this lead compensator and lag compensator, we use both of them in parallel. So this you may choose as lead compensator part, this we may choose as lag compensator part, alpha less than 1, beta greater than 1, and K dash is alpha beta K. And in frequency sinusoidal free transfer function looks like this as given here. These may look complicated to begin with, but as we go ahead, we try to use them often, and you kind of remember. If the numerator is heavy, we call it lead compensator. If the denominator is heavy, we call it the lag compensator. And lag lead compensator is a combination of the two. We write the open loop transfer function as compensator multiplied by the plant. And we saw that the compensator can be written as K dash into some dynamic part multiplied by G omega. But the way we use it is we kind of try to club this K dash and G together and then design GC. So we take this K dash G of J omega as one unit find the value of k dash, and then design this gc dash. It may look kind of confusing now, but as we go along, I think it will become clear. The details, but design process at a glance looks something like this. To meet the steady state specification, first consider and find what is this k dash. If this k dash solves your problem, your design is complete, and we stop here. If it doesn't meet the requirements, then we design this appropriately, either to increase the phase or to reshape the Bode plot to give required phase margin. So in summary, what we have done is we have seen briefly what is design in frequency domain and how does it look like. And we saw performance specifications both in time domain as well as in frequency domain, and saw the outline procedure. We didn't go into the details of lead or lag, which we will do in time to come. I think that's all we have now. Have a great day.